So our next speaker is Sangwin, who is a professor at the University of Edinburgh, and he is a specialist in the automatic assessment of mathematics, which I find pretty interesting. I don't know where it is, but that you can tell us about it. And also, he studies mathematics through student-centered approaches. It's also very interesting. So, Chris, please, thank you for coming.
Well, thank you very much for this invitation. The automatic assessment of mathematics, I write software that automatically marks students' homework.
Oh my God, I want it!
So you can talk to me about that later. That's not why I'm here. I am here to talk about board games. And in particular, I'm going to focus on one board game and one collection of related board games called Hex. So can I just have a show of hands? How many people have heard of Hex? Okay. How many people have not heard of Hex? Oh, so this normally when I ask the question of the audience, it's a threat to the law of the excluded middle, but I think nearly everybody answered that. All right. So there's quite a few people who haven't heard of Hex, and well, neither had I. And I was sad to say I'm very disappointed that I hadn't heard about it. And so I want to use this game of Hex as a model, as a toy, if you like, to follow Chris Budd's talk, for mathematics itself. And I wanted to do that as a way of engaging people in mathematics, using games as a way of helping in education. So whilst toys are often an artifact, it's a thing, here it is, a game is also slightly different because there's a social process involved. Okay, so there's a subtle difference in a toy and a game. So let me tell you a little bit about Hex, because there's a good number of people here who've never played it or heard of it. It's a connection strategy game for 2 players. And the goal is simple, that you have to link your sides of the board. So here's the Hex board, and as the name implies, it is played on a board consisting of hexagonal cells. And you place your counters, one side is blue and one side is red, and you place your counters inside the hexes, so you occupy the hex, so we're not playing on the lines, we're playing in the cells. And the goal is to connect up one side of the board by a continuous path to the other side of the board. Okay? So the reason for using my laptop is that there's a really nice, let's go for a smaller board. So I'm red by the look of it. I'm almost certainly going to lose very quickly. Yeah, I think I've already lost. So does this make sense? Let's just, there we go. So blue's definitely going to get one of those, and blue's definitely going to get one of those. So let's just finish the thing off. There we are. Right, so I lost. So does that make sense what the game is, everyone? It's blockbusters for those people that grew up in a certain period of time in the UK. There we go. So you choose a colour, players take turns. On each turn you place one counter in the cell. Pieces cannot be moved, okay, except for a rule which I'll talk about later. So pieces cannot be moved. And the 4 corners belong to both sides, just in case anyone's worried about what happens in the corners. And that's it, that's the game. So the rules are almost nothing to the rules. You already understand the rules. In terms of describing the game compared to other similar games, well, it's a game, so it's a competitive strategy, it's a competitive scenario with rules. That's what a game is. There are rules. No one can force you to play the game. You actually have to voluntarily want to play the game, right? You have to voluntarily agree to play by the rules. That's part of what a game is, right? When you say, oh, you're not playing the game, that's you're not subscribing to the rules. It's an important aspect of what is and isn't a game. In this case, it's a 2-person game, although when I've used this with students, I've often used it as a 2-team game, so that you have more than one person per side. It's called a zero-sum game because you either win or lose to each other. And it must be a finite game. Okay? The game must end. There are a finite number of cells, you fill them up and it's over. That's it. Right? The game must end. And it's a perfect information game. There's no chance, we're not rolling dice. There are no cards or hidden information. You can You see everything at the outset. And it's a strategy game. And for this reason, games and games of this type are often called connection strategy games. Right. So I've already shown you Hexy, a perfectly worthy opponent. And right, let's start again. Board size, let's do a slightly larger one. And you can get the thing to play itself, and off it goes. And for those people who've never seen this before, it's worth noting that you can place your pieces anywhere. I've watched lots of people learn this game, and it's fascinating to watch how predictable people are when they learn something like this. Okay, so that's the basic game. Did blue win? Yeah, blue won. Okay. Right. And so then you come to thinking, well, how can I learn this game? What is the basic strategy for playing this game? And the first thing to say is that you can place your counters anywhere, right? Not just next to each other. Typically, beginners just try and walk across the board. Just see it every single time. The other thing you have to do is respond to your opponent. I know that sounds obvious. People find that really hard. And then this is, again, entirely obvious to an intelligent audience. If you can think of a strong response to your own move, you have to look for a better move before you play it, right? This is a perfect information game. In a sense, the whole game is determined at the outset, right? You just search the tree of all, the space of all possible games. More strategic comments. In this game, you need to make connections between your pieces and block your opponent. That's really the key to this. And so defense in this game is also attack. You'll notice that there is a sort of symmetry between defense and attack. Creating a path blocks your opponent, right? So it's essential to do that. And this, I think, is one of the areas that beginners find most difficult, is to abandon areas of the board when it's completely hopeless, to actually give up on a losing strategy. And one of the definitions of creativity is the ability to switch thought. See, when you look at when people have tried to define what is creativity, it's not getting stuck, it's actually freeing yourself and moving on. Except what's interesting about this game is that a good game between well-matched opponents will switch backwards and forwards many times in a game. It looks hopeless, and then it switches, and now you look like you're winning. And so it's quite an exciting game to play. Cameron Brown likened this to a knife fight in a telephone box, because it's a very finely balanced game, and then suddenly someone wins. It's really interesting. I think this is really interesting. And one of the reasons I think I've decided I wanted to use this as a model for mathematics and a model for education is the perception of structure within the game, right? How do you learn something really complicated like this game? And I'm probably not doing it justice, but if you compare this to something like chess, because you can place any piece in any hex at any moment, there are many more combinations in this game than there are chess moves. How many opening moves are there in a game of chess? You can move the pawns, you can move, you haven't got that many moves, but on an 11 by 11 board, you've got 121 moves, right? So which do you choose? You've got to somehow narrow down this massive search space. And so you start looking for patterns. And this bridge allows you to get a lot further quicker than you might otherwise expect. Because however blue responds, however blue plays, red will get one of those two hexes, right? Okay? This is the first really logical observation. So you don't need to place your counters next to each other. You can place them further away, get further across the board quicker by using these kinds of patterns of play. So you can apply this reasoning to the edges. Whatever blue plays, these two hexes are unoccupied. They form part of this template of play. If blue plays there, red plays here, and so on. Okay, it's pretty obvious. And so this is typically what the beginning player does. If you play this with anyone, they always put the first piece next to their edge. They know they don't have to, but they always do. I mean, modally, right? That's what happens. Red, on the other hand, has gone bang, 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 and in 3 moves has won. Red will win. As provided they play intelligently from this point onwards, red must win. Yeah? So part of learning this game is seeing these kinds of patterns of play and realizing that these two are connected and these two are essentially connected and so on. Does that make sense? There's some structure within the game. There are patterns within the game. After the bridge, this is what I refer to as the 2-3-4 template. For obvious reasons, it involves 2, then 3, then 4 hexes. Now, I'm claiming that red, provided they play intelligently and immediately, is connected to the edge. Okay, if blue puts a counter in any of these hexes, red goes here and now has one of those two as well. So that means blue must play somewhere in here, in which case red places on here and has a bridge, the previous template, and an edge bridge, so red is now connected to there. Does that make sense? Yeah? So in fact, you don't need to place your piece next to the edge like this. You can place your piece even further away, and then you still win. And these templates get even bigger, right? Okay, this is actually just either red occupies this hex and has the 2, 3, 4 template, or red builds a bridge to this one and has the 2, 3, 4 template. In either way, red has got to the edge. Now, you attack templates mostly by, I said you have to respond immediately. You do have to respond immediately, right? So this, where I put the question mark, actually is part of both of those templates. So if blue puts a hex there, red can't go here and have this unoccupied template, and red can't go here and have this unoccupied template. Fortunately for red, if blue goes there, there is still a move that will allow red to get to the edge. Okay, you can puzzle that out on the train on the way home. Right? But the game very rapidly becomes a battle of overlapping templates, looking for structure within the game. Okay? And so that goes through phases. Now these are logical puzzles within the game itself, right? There's other sort of vaguer sorts of thinking. Oh, and here's a puzzle template for you. Why is red connected to this edge? There are lots of these, and you sort of have to remember them if you're playing. And then there's sort of fuzzy thinking, not just looking at these defined logical puzzles, but heuristics. And again, heuristics are really important in expert behavior. How do you determine an expert? Experts have these heuristics. One of the heuristics in the game of hex is to look for the weakest link in your opponent's strongest chain. Okay? That helps you reduce the search space for the place you need to do to block them and connect up your pieces. Right? So these kinds of vaguer kind of heuristics are part of becoming an expert. I was fascinated to learn that this game was only invented in the 1940s, and even more interestingly was simultaneously invented independently, firstly by Piet Hein, the Danish mathematician, and by John Nash, the American. Right? We talked about, Sir Michael I think talked about history and connections. These things happen all the time. It's fascinating to me that this has happened. Such a rich game was reinvented in a short... yes, thank you, yes. So those, we've already seen there are puzzles within the game, but there are also puzzles about mathematics about all games. Right? So what, as a mathematician, you want to ask questions not just about how to win a particular game, but can we ask questions about every game? Can games end in a draw? These are questions about all games. It's a non-trivial question. If you play exactly the same game on a square board and don't connect up diagonals, you can easily end in a deadlock, right? There's no way we have defined that cells are connected by a proper edge. These are not connected, right? That's we've decided that as a rule. Under that interpretation, this game can't be won. But that's not true of hex. Hex never ends in a deadlock, and the way these games are analysed is via the connectivity, the topology of the graph underlying the game. So the one way to abstract the game even further into a mathematical formulation is to put nodes in the cells and draw edges between the nodes indicate that nodes are adjacent to each other. And then you play the game on the graph by occupying the edges, right? So you change the game. Okay, and so that leads on to a whole bunch of variations of games played on different graphs. You can change the board size. I already showed you that. There are other rules. The first person to connect their sides loses, for example, right? Somebody must win or lose. There you go. So you can play all sorts of games. You can change the shape of the board and have very different boards, and you can alter the connectivity. And actually, most of these things, I won't talk too much about this, can be abstracted as something called the Shannon switching game. So if you want further information about this, that's a good place to start. The game of Y, for example, is played on this board. The rules are identical, but the winning condition is that you have to connect up all three sides. Okay? Now, in hex, you have sort of complementary goals. Somebody's going across one way, blue's going top to bottom, say, red's going across horizontally. In Y, both people have the same goal. Both players are trying to connect up all three sides in one continuous path. And it turns out that actually hex is a special case of Y. Right? Actually, when you look at the maths of it, they are the same, exactly the same game. And Cameron Brown has written this excellent book where he analyses, I will say hundreds, but many, many games, and illustrates the mathematical similarities and mathematical differences between board games based on the underlying connectivity of their graphs. Really fascinating subject. Normally, of course, you obscure all this, right? You know, when you're inventing a game or playing a game, you're not aware of this. Has anyone seen Dobble?
Yes.
Yeah, this, if you've got 5 or 6-year-old kids, this is just a fantastically fun game to play, quick fire game. Dobble consists of these round cards, and each of the cards has these symbols on it. So there's a heart, a maple leaf, an eye. And basically, each pair of cards has precisely one symbol in common. They're a fascinating piece of finite geometry, beautifully obscured in this wonderful game. Right, so one of the reasons I chose hex as an outreach and engagement thing was because of the clarity of the math in the game. That was precisely a characteristic I wanted in the game for my purpose. But mostly it's obscured for other very good reasons. So beyond its intrinsic fun, I chose this as an engagement activity. To, just as Chris Budd has talked about engaging the public, I wanted this as a model for learning a skill, if you like, and a model for developing expertise, and as a social process. I was interested in helping people understand the structure within the game. Actually, if you get good at something and interested in it, you might be interested in about all games. Is there a winning strategy? And if so, what is it? Because I'm interested in teaching mathematics. So what I'm claiming this connection between something like a game of hex as a model for mathematics and mathematics itself. So this is a puzzly thing, which came up on one of these social media things. You know, you get a puzzle for the day or whatever it is. And this was one of them. Came up a couple of weeks ago. Find 3 consecutive integers, x, y, and z, which satisfy this equation.
1, 2, 3. 1, 2, 3.
Minus 1, 2, 3.
All right. Yeah, so, you know, yeah, so you can spot these, but if you want to systematically find all of them, what might you do? Well, this might be one naive approach, right? n plus 1, n plus 2. And already you're thinking, oh no, I've got some hideous cubic to solve here when I've rearranged everything. But thinking ahead, a hallmark of expertise, and I make no apologies for choosing a very simple example here. If you choose n minus 1, n plus 1, if you can think what comes next, you immediately see that this results in there's really no equation to solve now. It's not some hideous cubic. There is a transparency here. You know, as mathematicians and experts, we know we think ahead, right? And that's a very difficult sell to students. You have to become, if you want to be successful, you need to develop a skill to a level of expertise where you can see ahead. It's not the doing the thing, it's the things that come after that. Knowing why you've made this choice, n minus 1, n plus 1, rather than n plus 1, n plus 2. It looks completely trivial to experts, But the hallmark of expertise is that they generally make things like the second choice and not the first. So just as in the game of hex, looking ahead is vital, so I think is in mass education. So these patterns of thought recur again and again. I took this from proofs from the book. Some of you will be familiar with this wonderful book. Alice looks at Bob and Bob looks at Claire. Alice is married but Claire is not. Prove that a married person looks at an unmarried person. Right? So just for notational convenience, I've said Alice is married and Alice looks at Bob. We don't know about Bob, but Bob looks at Claire. Right? So we've got to prove that a married person looks at an unmarried person. And it's not transitive, so you can't say Alice looks at Claire. Right? That doesn't work. Right, so Bob is married, then Bob looks at Claire, we're done. If Bob is unmarried, Alice looks at Bob. So we can prove that a married person looks at an unmarried person, but we don't know which of the two possibilities actually occurs. Yes, so it makes a slightly uncomfortable sort of thing. You have to believe in the law of the excluded middle and some other logical things like this to make it all work. But there you are. Now you think, oh, this is a silly puzzle and a silly trick. But actually it's not, as I've taken from proofs from the book. Prove that an irrational power of an irrational number can be rational. Right, so root 2 is irrational and consider root 2 to the root 2. Is it rational? Yes, we're done. No, root 2 to the root 2. This is an irrational number to an irrational number. It's just root 2 squared, which is 2, which is rational. So an irrational power of an irrational power can be rational. Yeah, we just don't know which one it is. Okay, so what looks like a silly puzzle is a pattern of thought which is useful. And I did some work with some chemists. The chemists wanted their students to become better mathematicians, and they wanted to do it through puzzles. And so we tried to come up with puzzles, and I thought through this puzzle-based learning approach, thought about what is a trick question. What is a trick question to our students? And my working definition of a trick question is that it is a question for which there is a unique intellectual move which allows you to answer that question. And as of yet, I haven't found any trick questions because intellectual moves are recycled all the time. Of course they are. If they're useful for something difficult, then you're going to recycle them. Unfortunately, we know from psychology that actually transferring things from one place to another is extremely hard. People generally find that, in most cases, impossible for them to transfer something from one situation to another. That's precisely why mathematicians abstract things. So hex was more or less successful, but not uniformly so. Right? And I think it was quite a polarizing activity. I'm not going to stand here and claim this was a complete success, because actually it wasn't. There were some people, and I ran this at a science fair with 400 students playing on 100 boards in groups of 4, so 2 per side. The idea of having 2 people per side was that they would have to talk about their strategy, thereby giving away what they were thinking to their opponents, who, if they were a little better, would have seen it anyway. Right? Okay, so. And for some people this was a deeply off-putting activity, partly because people don't like to lose. Right? And that's a perfectly reasonable human emotion, isn't it? Some people enjoy competitive situations, others don't. That's just part of it. And so I think it was not entirely successful, but there we are. That's just the reality of it. It's very interesting to watch people outside their comfort zone. One thing I would say in favour of hex, unlike some engagement activities, that like many people here, the students who come to this game have never seen it before. So the precocious, bright person who happens to have spent more time doing maths is not initially at an advantage when they're doing a game like this. So even though I've used it to communicate things about mathematics, i.e. trying to talk about all games, not just the game you're playing, the kind of things mathematicians do all the time, it was a leveler. That was one of the reasons for choosing it. There's some very interesting philosophy about the nature of games and the nature of play in society, and here I am stepping outside my comfort zone a little, and certainly outside my area of expertise. But I do want to say a few things about what is a game. You see, mathematical competitions, in a sense, are a game, right? They are games. We play games in society. We play games, not just a board game, but bigger games like the exam game. I'm going to go, in a week's time, I will have 600 exam scripts to mark. Right? My students are playing an exam game. They've chosen to play that game, right? They're not forced to come to university. They're not forced to play that game. They have accepted the rules and they're playing the game. It is a game, according to some social definitions of what is and isn't a game. And there have been I have arguments going back 400 years on whether we should allow students to use calculators, for example. To what extent do people have to do things themselves? All these things go on. And this quote from Cass, I think, for me, is really helpful. To be trained is to be prepared against surprise, and to be educated is to be prepared for surprise. Right? We do need to get good at certain stuff. We need to learn stuff so you're not surprised. I'm sure some of you were looking at that cubic I put up and went, that's trivial, it's completely trivial. Well, that's not on the A-level syllabus to solve, cubic equations. They're not usually in that form. They're usually written in a much more convenient form, all on one side before the student sees it. So why get good at something? If you want to get good at it, you have to do that thing. Malcolm Swan talked about having tests worth teaching to. And now I'm really getting political. If we're communicating what the nature of our subject is and how we judge success in our students, then we need to be really careful that the exams that we set, the game they're playing, accurately reflect what we want them to be doing, right? That's the game, that's our part in the game. We have a part to play in that game. So, yeah, back to something more pleasurable and fun, board game afternoon. These games, there are lots of them and they have a lot of structure, internal structure. There are similarities between the games. I think they are slightly problematic as an engagement activity, and I encourage you to try it and encourage you to pay attention to those problems. I don't think they're insuperable, but we just have to watch out for that. Board games in general are hugely engagingly fun and popular, and if you've never played Hex, then have a go, because it's great fun. So thank you very much.
Questions?
I have a game-related question. There's a game called Risk that combines those types of making links because, well, I guess you know the game.
Yep.
With additional complications where you have to fight an army, etc. I wonder if you have ever used Risk as a...
I haven't used Risk and I haven't analysed it, so that has some dice rolling, doesn't it?
Yes.
Yeah. So there's some element of randomness. Certainly, when choosing a game as a model of mathematics, I wanted something with clarity and simplicity and no chance. So I wasn't looking in that direction.
Naively, if somebody's never been exposed to Hex, it would seem to be a big advantage to go first from what you as you described it. But can you prove that's not the case?
I've kept a lot of the maths out of here. So Nash came up with a strategy stealing argument, and his strategy stealing argument says the first player must win. Now, there is something I referred to very briefly called the swap rule. Right, the swap rule later, which now is my good later chance. I knew someone would ask about this. On their first go, the second player can either play normally or swap with the first player's move. So if the first player takes the middle hex, the second player can go, no, I'm going to have the middle hex. If you have the middle hex, I'm going to take it. So it's not then clear that what the first player should do. There's no point explaining the swap rule to a novice player because they spend half an hour worrying about where to place their first hex without ever placing a counter, right? So if you're introducing this game, just forget about the swap rule, okay, until it's blindingly obvious that on a small board the first person's going to win. And then you can introduce the swap rule because people have had a bit more experience. The swap rule destroys Nash's strategy stealing argument and actually makes the game more fun to play.
I just thought our long-term participants might like to know that actually a number of the games that we mentioned today we have upstairs for participants and their children to use. So for instance, IQ Pro, which is the knapsack packing one that Chris talked about earlier, we have that one. We've got Rummikub, Chocolate Fix, which is a divine logic reasoning game. So those of you who are here for a while, or indeed those of you from CMS who just fancy coming and having a go at some of these games, we just have them upstairs and you're very welcome to use them.
Yes, thank you. And I think last time I was here in the summer, I abandoned a hex set upstairs, so there should be a hex board in the building. I hope there's still a hex board in the building.
Any other questions? But if not, thank you.